Now we will talk about the independent events. In the previous topics, we covered where we had the mutually exclusive events like this, like if some event A happens, the probability of B happening would be 0. It means that they block each other. And those cases, like if A happens, we are sure that B happened. It means that now in this sense, event A would be a subset of event B. Now, we covered these, the mutually exclusive events and subsets of events. However, what about the independent events? In fact, many daily events do not have any effect on another. This is called the concept of independence, where we can have knowing the outcome of one of the events, let's say that it is event A, does not have any effect on the probability of happening of event B. Suppose that we're rolling 2 dice here. Now let's take a look at this together. So here, suppose that we roll 2 dice, and let's define event A as an even number, for example, an even number on the first row, okay, and our event B would be corresponding to getting, for example, 2 or 3, okay, 2 or 3 in on the second row, okay, second row. Now, normally those events do not affect each other. That's the idea. So when you want to write probability of B given A, this comes from the definition of conditional probability, right? So we know that PA is 18 over 36. How do we find this? I mean, remember that we had this 2 dice examples here. I hope you remember this sample set, right? From here, from the sample set of 36 elements, that's how we define it. Okay, half of them would be covering an even number on the first row, no matter what you get in the second row. And how about the probability of B here? It is only the 12 cases, and given the full sample set of 36 elements here. And I know that probability of A intersection B is only 6 events over the sample space of 36. We can easily find this with the multiplication method, right? That we discussed a few moments ago, like you know, both of them happening at the same time. That's the idea. So now, I mean, if you want to write this probability of B given A, it should be this one over this one, probability of A, right? Coming from here, this one, that should give you 1 over 3 as the result, which is your probability of B. In fact, you see, look at this. This is in fact your probability of B, directly equal to this. If you can write the expression or equation like this, if this equivalence holds, it means that A and B are independent events. So terms do not affect each other. So that's the idea. So this is called the concept of statistical independence. Okay, so if this one holds, this one holds, we're talking about statistical independence. Okay, B. See, if this one holds, A and B are statistically independent from each other. We can give some examples, some more examples about this in a graphical manner, which could be more expressive, hopefully. Suppose that you have two parts of a components of a device, for example. Both of them should be working so that this device works. Okay, so the probability that it works is the same for both of them. Let's suppose it, it would be probability of C1 works intersection C2 works, right? You can write it like this. So let's suppose that the probability of being broken is represented with small p, for example. The probability that a component is broken. So it means that I need to have what for it works? Probability that the device works would be 1 minus p times 1 minus p, right? So not being broken, the probability of not, this is for C1 and this is for C2 here, and the result will be, not surprisingly, 1 minus p over 2. You can generalize this for more than 2 events, like this. Probability of A intersection B intersection C. What should it be? It should be probability of A times probability of B times probability of C. All right. So that's the idea. Suppose that we just focus on another setup like this. Again, a device example here. So here you will have switching mechanism like this, and here you have 4 switches. Okay, suppose that you're trying to get this device working or get this system working. So the probability that any of the switches would be closed would be represented with P. Suppose that we will call this P, and let's give some labels to those switches. Let's say that this is 1 and this is 2 and this is 3 and this is switch number 4. So what is the probability that you will have voltage? Suppose that this is a circuit or a system between the two ends of A and B points of the circuit, for example, or device to get working. It should be C1 intersection 2. Either that path should work or the other one. Okay, so how do you depict this? How do you show this? This one and C3 intersection C4 and their union, right? So they're not, canceling or stopping each other, so they're not blocking each other. Okay, and the probability of E would be probability of C1 intersection C2 plus probability of C3 intersection C4. Is that okay? So both of them could be working at the same time too, right? So we need to subtract this intersection for once. So that's the idea. Probability of C1 intersection C2 intersection C3 intersection C4 should be subtracted from it for once, and the remaining part would be just a calculation. So it should be p square plus p square minus p over 4. So these would be corresponding to those ones, this one to this one, this one to this one. So, and the result will be what? 2p squared minus p over 2 p to the power 4. So this is the idea about the random variables here, where you can have concept of independence. Now, your random variables can be qualitative or quantitative in nature. Suppose that if you're talking about the weather condition, it's it's clear that it is qualitative, right? It is whether it is sunny or it is raining or it is cloudy, whatever. So it's a qualitative variable. And daily production of grain, for example. So it means that this much of kilograms or something like this, daily production. So it corresponds to a quantitative variable. So your variables can be either qualitative or quantitative. And the observed variables are depicted with X, Y, Z capital. Just capital letters of the alphabet. And each element of sample space can correspond to only one X value here, such that any random variable here can address multiple elements in sample space as well. Now let me try to show you this on the board so that you can have a brief idea about it. So suppose that you have your random variable X here, and suppose that your X is the number of heads in 2 coin tosses. Okay, that's what we're dealing with. And on the X variable, what you can have as values, you can have X equals 0 or X equals 1 or X equals 2. That's it. That's what you can have. And what do you have in the sample space here? These are your even elements of sample space. You will have namely 4 elements here where you can have like heads, 1, tails, heads, tails, heads, and tails, right? So you can have setup like this, and as you see, so you correspond all of them to the values here in the it's a matching. Okay, it looks like a matching here between those elements to that random variable X here. Okay, this one corresponds to this one, and this one corresponds to this one, and the remaining ones are corresponded to this one. Okay, we're just doing a matching here, right? Matching here between them. That's what we're talking about. It's like it works like a matching approach here. So this is what we're told in the slide as well. In other words, a random variable is a function that mathematically assigns values to the elements of the sample space. Now, when we look at the categorization of the random variables, if there are infinitely many number of elements in sample space, it might be impractical to assign a probability value for each of the elements. So it can be meaningless, okay? And for example, the daily random drop values, for example, okay? No need to, you cannot count the number of options you have here. But eventually, they would add up to 1 because it's a probability, okay? All of them a theoretical value, okay? And if the elements of sample space in this sense are countable, they're called the discrete random variables, okay? If you can count them, go ahead, okay? They're called discrete random variables. But if the elements of sample space are uncountable, impossible, they're called continuous random variables. That's the distinction. Now, let's go ahead and talk about discrete random variables first. If a random variable can have specific number of values, for example, the number of bacteria in a particular container of water, or the number of defectives in tens of samples of a production, or the number of incoming calls to a call center in a specific time, or the number of patients in the doctor's waiting room. You can multiply those examples as long as you want, but this is the idea about the discretes. Suppose that you're talking about the number of defectives in a production facility in tens of groups, defectives in tens of samples of production here. You define this y as the random variable. See, it is capital, and these are the possible different values of that random variable. Is depicted like this: 0, 1, 2, 3, up to what? Up to 10, right? Because you have 10 packs here, 10 of them could be possible, and here you can have 11 different values for y random variable here. Or suppose that you're talking about the number of bacteria in a particular water container bacteria, or 1 cubic centimeter of water here. Again, this time your capital X would be your random variable here, and your X will take values between 0, 1, 2, up to what? So it is n. It can have infinitely many, right? But yes, but still it is a discrete variable, but it can have a real high ceiling value, but still a discrete variable, because you cannot put infinitely many elements here between those elements. If you can put infinitely many elements between those every element, it means that you're talking about a continuous variable. Otherwise, as you see here, now although it can have a really high ceiling value here, it is still a discrete random variable that we're talking about. Okay. Let's take a look at the properties of the probability distribution of discrete random variables. And if you look at it from our textbook as well, and they give some examples with the two coin tosses again. Or okay, popular example here, two coin tosses example here. And suppose that you're dealing with the number of heads in those two coin tosses, and if you want to summarize this in a table, you will have here namely four different elements here where you will have your first coin and the second coin outcomes, like okay, tails, okay, heads, tails, heads, and heads. All right. So, and they're here corresponding probabilities here would be given here like I. They would be like 1/4 and 1/4 and 1/4 and 1/4, not surprisingly, right? And your random variable x will take values of corresponding here you see, means that you just count the number of heads here, that's it, and that's how you create this table. Now, as we see from the table, you can write it directly like this for any given random variable. Probability of x equals 1 would be probability of E2 element plus probability of E3 element, which would give you 1/4 plus 1/4, 1/2. You can also, see that if you add all of them together, the probabilities from I to 1/4 probability of EI should be equal to, from x0 to 2, probability of random variable x, both of them should be equal to 1, right? This is obvious from the table. As you see now, px is just a function of x, in fact, and you can also take or extract this probability function here, like it is 1/4 root combination of x here, where your x can take values 0, 1, and 2. So when you put them in their corresponding positions here in the equation, probability of 0 would be 1/4 combination of 2 and 0, and probability of 1 should be 1/4 combination of 2 and 1, and probability of 2 should be 1/4 combination of 2 and 2, and the results would be 1/4, 2/4, and 1/4. Again, we will take a look at how we derive these formulas in further examples as well. Now, you can also depict this in a table as well, like in just a different view for you to have an idea. Your random variable here is set on left, and your samples here, corresponding samples here, like E1, E2, E3 here, so E4, and their corresponding probabilities are given here as well, 1/4, 1/2, and 1/4. Not surprisingly, Okay, this is your whole possibilities, and this is 1, and this again correspond to total. Okay, these type of discrete variables can also be depicted with the histogram, like bar graphs. I'm sorry, with the bar graphs, like you will have here 0.25. This is your px y-axis, and you use the x variable value as the x-axis here, and here you will have 0 and 1 and 2 as bar graphs. So you just put their corresponding locations here, and the result will be something like this. Okay, these would be your bar graph representation for these 2 coin tosses as well. Now, if we repeat this 2 coin tosses experiment for, let's say, 100 trials, and we construct a bar graph like this, it would look more like this bar graph. If we increase the trials to, for example, 1,000, it would even look more like this ideal bar graph. So suppose that you change the nature of the experiment like this. You toss a coin until you get the first tails, for example. Okay, how can you write the elements here in this sample space? In this sense, you toss the coin until you get the first A. So what could be your elements here? 1 should be directly getting the tails, right? The first one would be this one. And how about event 2? It's the first one is heads and the second one is tails. And event 3, heads, heads, tails. And event 4, heads, 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 tails. It goes like this. What? To infinity, right? Infinity. If you write the probabilities of those elements here, corresponding values here, it would be 1/2, 1/4, oops, like 1/8, 1/16. Okay, goes. If you had, for example, E5 here, what should it be? Heads, 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 tails. 1/32, for example. Okay, goes like this down. And what is the corresponding x variable here? How many trials you do until you get the first tails here? It is in the first trial, 2 trials, 3 trials, 4 trials, and 5 trials. And here you see the probability of x is again exactly this event happening here. Now, if you have this condition here, like your probability of x should be between 0 and 1 here, if you add them up until infinity, if you apply the limit here from x1 to infinity here, so you send your trials to infinity here, it should be probability of 1 plus probability of 2 plus probability of 3 plus, okay, 3 trials plus up to probability of infinity, right? So infinity, So it should correspond to 1 over 2 plus 1 over 4 plus 1 over 8 plus dot 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 dot. So the total, when you apply a limit theorem here, the total of this value would be equal to 1. I think we also talked about this in in our previous session that I addressed you to watch a professor's video for more detailed explanation of this trial, okay, if you remember it. You can go back and watch that video again. Okay, these are all about the properties of the probability distribution of discrete random. Now, let's talk about the continuous random variables here. If a random variable can take infinitely many number of values, it means that there will be infinitely many number of elements between elements here, then they are called continuous random variables. Those type of variables strictly depend on the sensitivity of the measurement tools you are using, of course. If you're, for example, measuring your height or weight or something, it is directly affected by the sensitivity of your measurement tool here. And now here you need to rely on relative frequencies of observations here. Again, this never changes. The higher number of samples you have, the more precise the distribution would look like. Now let me try to show you this with the graph in the textbook. Suppose that you have an fy continuous variable here, and this is the y that it takes. So it's a relative frequency distribution for a population here. Here you have this. Okay, oops, not so. Okay, something like this. And if you define an fy as a continuous random variable here within that population, it would look like this from, for example, A to B here, like the probability of A between A and B. We're talking about the area under the given curve here, right? So I mean the thing is, like you will have like your probability of y should be again between 0 and 1, and all y, when you add them, all of them up, you will end up with 1. So that's the idea here. Okay, with the I mean continuous random variables. Okay, how do we choose fy function here? Okay, the fy function, or how to calculate the area below that curve. You can rely on the integrals or readily say available. You can also use the readily available tables for this purpose. So I mean these are your options. And there are also methods to check whether the selected fy and the real relative frequency curve of the population are relevant with each other as well. We will discuss this in chapter 3 hopefully, so that you can have more idea about the the fitness or the possible alternatives, deciding between the different alternatives of modeling a given population data set, for example. Now we will talk about an important topic which is called the expected value. What we do here is, namely, calculating the mean value of a function defined on a theoretic population here. That's what we're trying to do. Let me try to do this or explain this with an example to you again, our famous example. Let's say that we have two coin tosses again, and we're dealing with the number of heads here. I write it again, two coin tosses, and number of heads is what we're dealing with here. And here we define our x variable can have 0, 1, and 2, and their corresponding probability of x variables here, 1 over 4, 1 over 2, and 1 over 4 here. I think we're familiar with this already from the previous slides. If we repeat this trials for many times, suppose that for 4 million times, we're talking about 4 million trials here, what would be the average value of x here? Okay, so it would look like this. Your total measurements over n, right? Number of the trials here. So, and what would be those values? Okay, 10 to the power 6 times it would be 0 plus 2 times 10 to the power 6 times, you will get here 1 plus again 10 to the power 6 times, you will get 2. Is that right? Yes, I think it is right. Look at this. It is coming from the I'm sorry. So it's from this one, and this one from this one from this one, right? So, and if you write the 4 times 10 to the power 6 here, you will end up with 1 over 4, 0 plus 1 over, 1 over 2 times 1, it should be 1, plus 1 over 4 times 2 over, that's it. So what you have here, this one, and it would correspond to 1. So this is the average value of having heads and 2 coin tosses. So you're expecting, this is your expected value. This is your expectation about that particular event. So you can write this. You can, if you add from 0 to 2, x times px give you 1. You can write it like this because you added all the possibilities here. You can generalize this for any population. Like suppose that you're talking about the population average here, which is the expected value of x here. It should be the total of all x's multiplied by its probabilities in a given population added together. This is for what? For discrete random variables. And if you had a continuous variable. Here, in this sense, you need to calculate the area below those curves with the integral or the integral tables here, but we will not go in detail of calculating those values in doing integrals here. No need to do this, but you should keep in mind that this is the case for continuous variables as well. We will talk about this a bit more in chapter 3, hopefully. So let's try to solve an example here so that maybe it would make more sense. Suppose that there is a lottery here, defined lottery here, and there are 8,000 tickets for that lottery, and each ticket costs $1, for example. Okay, each ticket costs $1, and the grand prize is, let's say, the grand prize is $3,000. This is the grand prize, and this is the game. And suppose that you buy two tickets. Suppose that you buy two tickets. You buy two tickets for this lottery. What is your expected gain in this game, right? It's now here you need to first define your discrete continuous variable here. What you can have here, you can either lose your ticket price or win the grand prize. That's it. You either win the grand prize or you lose your ticket values. These are the possible options for your random variable. And what are the probabilities for this one? Let's say that it's a fair lottery, so it would be this much of probability you will lose $2. For this much of probability you will gain $2,998. Okay, like so if we go ahead and try to calculate the expected value of y here, multiply them with their multiply the random variables with their corresponding probabilities here, and you will end up with -2 times this probability plus times 2 over 8,000. Okay, when you make the necessary calculation, you will end up with minus $1.25. Okay, 1/4. Okay, 1 1/4. Loss is what you're expecting here. Okay, this is about the concept of expected value. But now we're always talking up to now we were always talking about the expected value of a random variable. You can code them. You can find the function, find the expected value of a function of a given random variable as well. Suppose that you're dealing with y squared or y minus mu square or something. It means that you're generating some functions from the expected value of a random variable here. So let's suppose that we return to our 2 coin tosses example again. So the variable will take values suppose that again number of heads is what we're dealing with, and your x is like this, and suppose that you define a function here for x. It is, let's say that x squared. Okay, now if you want to write down the expected value of this, or create this function here, x squared, and the probability of x here, so it would be again 0, 1, 2, but now you have a coded or a generated function here. It should be 1, 0, 1, and 4 here, and their probabilities are exactly coming from our random variable. Okay, these will match, right? These will match. They're constant or something, but this is generated one. Okay, this is what we're dealing with. And if you make the again the same calculation with, for example, 4 million trials, you remember, okay, all total over like n, if you, let's say that it's 4 million again, 4 million again, so you will end up with 1 over 4 times 0 plus 1 over 2 times 1 plus, and 1 over 4 times, this time it is 4. This is the only part different here because it's coming from the difference here, and the result will be from x0 to 2. Now it's the x squared here, probability of x, and the result will be 1.5. So with this generated functions g, namely gx, expected value here. So this is for a discrete random variable. You can also have the same generalization for continuous random variables as well. If it was a continuous random variable here, oops, oh, I'm sorry, it should look like this. Gy should be the area under the curve, Gy, Py, and so your E G Z would be the integral Z G Z let the Z here. So like this is the function that generated from our continuous variable. Let's solve one more example here. Now let's try to calculate the variance of our, again, 2 coin tosses example here, because we need coding for this, like 2 coin toss and expected number 2 coin tosses and expected number of heads in those 2 tosses. That was what we're dealing with. Your mu should be Ex should be like when we made the necessary calculations, it should look like this, and the result was what? 0 times 1 over 4 plus 1 times 1 over 2 plus again 1 times 1 over 4, and the result was 1. You were expecting 1 head and 2 coin tosses. Now your variance will be x mu square, x minus mu square here. So your variance should look like this. Expected value of this generated function, x minus mu square, will look like this for all x's, x minus mu square, and their corresponding probabilities, right? And they should be 0 minus 1 square times probability of 0 plus 1 minus 1 square probability of 1 plus 2 minus 1 square probability of 2. These are coming from the original random variable. You remember where are they? Yeah, look, the original is always fixed. See, the originals are always fixed. That's what we're talking about here, and this is important. So it should be 1 times 1 over 4 plus 0 times 1 over 2 plus 1 times 1 over 4, and the result will be what? 1 over 2. This is your variance. That's the idea. And now one last example, just a random example for practice. You don't have any meaning here. Here you have a y variables probability distribution given here. This is your given question. We'll have y random variable and probability of. It can have the outcomes of minus 1, 0, 1, and 2 respectively, and their corresponding probabilities should be 1 over 8, 4, 3 over 8, and 1 over 4. This is just a random example, okay? That doesn't have any meaning, but this should have any meaning, okay? When you add all of the possibilities here, they should correspond to 1. Now, when we are being asked to calculate any given function here based on this random variable, for example, this one, it would be rather straightforward, right? So you will just again work with the original table, but it would have a manipulation on it. The probabilities, that's it. That's what you have here. And the result will be what? Okay, it should be minus 1 square minus 1 probability of having minus 1 plus 0 square minus 1, have this one, probability of 0. Okay, have your 0 here, plus, and what you have here is 1 square minus 1, and okay, probability of 1 here, plus, and okay, you will have 2 square minus 1 and probability of 2 here. Okay, how did we get this? Let me just try to show you. Okay, okay, I'm sorry, let me choose another color. This one is coming right here, and this minus 1 is this one, you see, and the probability is coming from here, right? Probability of x is coming from right here. Great. So that's the idea. And how about this? You're okay. 0 is coming from here. Why it is square? Because it's square like this here. See, I tried to write it. And how about the -1 here? Again, it's coming from the function here. That's one. And where is this coming from? This is coming from right here, the probability. That's the idea. And what else? Okay, let's just do just one more time, and that's it, and that would be enough. Okay, where is this coming from? This is coming from here. And where is this coming from? It's coming from here, from the function, and the probability is coming from right here as well. Okay, one last time. Okay, this one is going to square here, and -1 is coming here, and this one is coming from right here. That's the idea. When you make the necessary calculations with your calculator, the result will be 0 times 1/8 plus -1 times 1/4 plus 0 times 3/8 plus 3 times 1/4, and the result will be 1/2. In fact, calculating the expected value of functions helps us to make some decisions for any situation, any case of scientific or economic investment or whatever. Okay, you need to know the expected value. Just imagine you're playing a lottery, or just you're playing a game of random variables, for example, anything. So it's very important. But to calculate the expected value, we need to know for each and every one of the samples and their corresponding probabilities to calculate those expected values of that random variable or any function of random variable, calculating the expected value of any function of that random variable as well. But first we need to know the elements and their corresponding probabilities here. Okay, this was all about chapter 2. You can go ahead and solve some examples on your own from the end of the chapter. There are very nice questions here at the end of the chapter. And thank you for listening.